Hi, welcome back. If you've seen any of my radio restoration projects on the channel, you'll have seen me use a lamp limiter with all these lamps and these switches on it. Now, this is obviously not the one that you've seen before. This is the deluxe version, and I've had quite a lot of requests for the schematic and instructions on how to build that, but I decided to build a new one and document that here. And the reason I built a new one is I wanted to take the concept one step further, because I had the dim bulb limiter, current limiter, but I wanted to put an isolation transformer in as well, which this one has got, as you may be able to see down there. So let me show you how this works, and then I'll explain to you how I got to this, and I'll show you some of the innards of the build. The idea of the lamp limiter or dim bulb tester is to create a lamp load in series with the load you're testing. If I put a light bulb, forget about these three, let's take one light bulb. This is a 60 watt light bulb. If I put that in series with my radio supply, and if there is a short on my radio supply, an absolute short, then the effect will be like switching on the light bulb. So that means that the current that will flow through a dead short will be the maximum current that would flow through a 60 watt light bulb. And because we use 230 volts here, that means that the maximum current that would flow through a 60 watt light bulb is about 250 milliamps. Is that right? 60 watts? Yeah, about a quarter of an amp. And that means that only a quarter of an amp will be able to flow through my defective radio. Therefore, it won't blow it up, and it won't necessarily create major fireworks. Now, the idea is that you can put in a 60 watt light bulb, a smaller light bulb, a bigger light bulb, whatever you want really, if you have one socket. What I decided to do is to create this where I have 4 sockets, and I can actually increase the number of bulbs that I have in there, and therefore increase the amount of current that can go through. So what that means is, when I switch this on, I'm putting this lamp in series with the load. When I switch that one on, I'm putting those two in parallel in series with the load. So if I have 40 watt in series with the load and I put this one on, I now have the same as 100 watt light bulb in series with the load. But I can go further. I can put another one of these that makes it 140, and I can put the last one in, which makes it 200 watts in series with the load. Meaning if I had a 200 watt light bulb in series with my radio, it's the same as having these 4 in place. Now the reason I chose these values is I can go up, I can go 40, I can go 60, I can switch that off and go 80, I can then go 100, 140, 160, 200, etc. That is why this is the deluxe version. Now, the way you do this normally is you'd put them all off, or you'd put the lowest one on. You'd make sure that it's on limit mode so that these bulbs are in series, and you would switch that on. What I have here is a little module that reads AC volts and current flowing into the load, and that is going to tell me how much current my load is drawing. Obviously that current is going through the light bulbs as well. So at the moment I have this set with a 40 watt bulb. That's a very high restriction, so a very small amount of current can flow through, about 1/6 of an amp. So not much will be damaged if there's a dead short on here. Now let me switch on the radio and watch how that thing glows. And the reason it glows is that there's an influx of current as it charges the supply capacitors. So there's a lot of current flows through there, and that thing glows. And then it dims a bit, because what happens is the capacitors charge, and the heaters of the tube radio in this case are starting to heat up, but there's not much anode current flowing through the tubes, so that sort of goes down a bit. And then as the current starts flowing through the tubes, that starts glowing as well. So let's try it. It got bright and it got dim. And I'm not sure if it's very clear on the video, but as those tubes start warming up, that thing will go brighter. And what we have at the moment, see, that's going slightly brighter, right? And the radio's turned on. I'm leaving it on and I'm putting the volume down. What this means is that the amount of current flowing through that light bulb is 120 milliamps, 0.12 amps, and it's splitting the voltage, the supply between the light bulb and the radio. And the amount of voltage that's going to the radio at the moment is 178 volts. Now, as I mentioned, I'm in a 230 volt system, so that is not half, more than half, but it's not the full supply voltage. Now watch what happens when I put another light bulb on. Watch that voltage. I put another light bulb on. Those two get dimmer because the current is now flowing through two of them, and that voltage goes up. 206 volts now. If I put another one on, you won't even see a flick, but it'll be 3 light bulbs. It'll be 140 watts in series. And again, the restriction is reduced. It's now 222 volts, 190 milliamps. And if I put the final one on, that's 226 volts arriving at the radio. And this thing is taking very small voltage drop. Okay. Now, what I can do is if I'm confident now that the radio is not displaying any shorts, I can bypass it. So if I do that, I have no current limit. The current is no longer flowing through those light bulbs. It's going through a shorting switch, and it's providing the full 232 volts to the radio. No protection at all, okay? That's why there's an exclamation mark on the bypass. And the radio is drawing 210 milliamps. So, again, this is how the system works. And as you can see, I brought it back down to maximum limit. In other words, minimum light bulb, and I've got 178 volts there again, and I can just switch the whole thing off. Very handy to have this available because sometimes you do see sparks and you want to switch that off rather quickly. One of the biggest risks of this is to switch it on with the limit but on bypass, so you have to be very careful with this. Now, the one I've used before, you've probably seen, was a lot simpler, it was a lot smaller, and it no longer exists because I cannibalized a lot of the parts from that one to apply to here, to use here. The sockets, the light bulbs, these switches are different. The voltage and current meter, that came from that one as well. The socket, a lot of the stuff came from the other one. But I'll now show you some of the insides, and then I'll discuss how this thing is developed and what schematic actually is used to build this. If we look at the back, you'll notice the main difference between this one and the other one. This is an isolation transformer. It is a 230 volts in, 230 volts out. It actually has two outputs, 0, 115, 230. The 115 I have no use for over here. So basically, the supply comes in, goes into the transformer, out of the transformer, and that's as if this was the new mains. Now, the advantage of isolation transformer, you can get a lot of information on the web. It's to avoid, to reduce the probability of getting yourself zapped when you're working with tube radios or tube amplifiers, guitar amps, whatever. But I decided to put it in here because this is the main test, the startup of any repair or any test that I do. And of course, I can then use this on the bypass mode just as an isolated supply without the dim bulb limiting. Okay, so we have the 4 bulbs over here. And if we can see this inside, it turns out pretty neat. These light bulbs come to a connector block over here. These connector blocks go to the switches. We'll see the schematic in a little while. All the switching is on that aluminum front panel, as is the little module at the back there, the voltage and current measuring module. Again, that'll be shown on the schematic. But those things are secondary. That's just an add-on to make this a deluxe version. And let me show you the front panel. I'll remove it as much as I can. Obviously, I'm not going to dismantle the whole thing, but it'll give you an idea. There's not really much that we can see because I don't want to pull the whole panel off. I would have to unscrew those connector blocks, and that really is a pain. So I will show you as much as I can. You can see all the switching is done there. The drilling of the front panel, the aluminum front panel, has got to be done very carefully so these things fit properly. These switches have an on-off and a neutral connection, and what that means is that when you have the on function activated, the neutral allows the neon bulb inside to light up. I like these because they give us an immediate visual indication of what's active and what isn't. The module down there, that's the module down there is the it's actually 400 volt maximum, I believe, 300 volt maximum AC voltage, and up to 10 amps. Because I wanted a lower reading, the current rating on this, the current sourcing on this is going to be a lot lower than 10 amps. Instead of winding one winding on that toroid, I did 10 and then calibrated it. You can adjust 2 calibration pots on the back there. So the meter's reading, say, 0 to 1 amp as opposed to 10 amps. The maximum current on this is going to be about 1 amp, because if I have 240 or 200 watts of light bulbs on 230 volts, it's just over 1 amp. So that shouldn't be a problem. And everything is wired very neatly. I use solid core wire that is big enough to allow the current to pass through, but you can wire it up very, very neatly, and it bends and keeps everything in place. Everything is soldered. You have to be very, very careful with this because this is mains. So here's the usual disclaimer. If you don't know what you're doing, don't mess around with this stuff. If you do know what you're doing, be careful anyway. This thing can kill you. If you don't know what you're doing, you shouldn't be restoring old radios anyway, because those things have very high voltages all the time. So be very, very careful with this. I don't want anybody to get zapped. And the other thing that's important to note is that the light bulbs are of the incandescent type. They are not the new energy saver ones. This is the typical old tungsten incandescent light bulbs, and it has to be that type so that the restriction works well on this. You can still get them in some places. I get them from some of the what you'd call dollar stores or poundland stores. They still have some of them lying around, and otherwise you go look at old light bulbs lying around, you'll still find incandescents. But anyway, this is a very quick description of the unit itself. And the next step will be to draw up this schematic and show you how the wiring is done. You have to know a little bit about what you're doing in terms of wiring. You've got to be able to take the schematic and put it into a wiring, physical wiring of a panel. As I said, if you don't really know how to do that, you should be very, very careful. Get someone who can, because you might get zapped. And the other thing about this thing, it's quite big, and this was done on purpose for various reasons. One of them is you've got the physical size of 4 light bulbs. If I wanted to put the bigger light bulbs, I wanted them to be able to fit. I happen to have these small ones, but they might burn out and I might need to replace them. So I needed a certain size. I wanted this closed in the top. The other one I had was light bulbs standing at the top, and anything would have broken them. So physical size came in. I built this out of MDF, 16mm MDF. And the biggest job really is building the enclosure. It's a pain in the butt. It really is, because you can't really get one of these things ready made. So cutting the wood, if you've got a workshop, it's so easy. If you don't, you really do have to put a bit of work into this. And the other reason why I wanted it to be quite big is because of the transformer, which obviously is quite hefty. This is a 350 watt transformer, so it can supply more than 1 amp. And this thing needed to be fit in here without too much fiddling around to try and get it to fit properly. I decided to give it its size. The other thing is you'll be plugging in equipment into the side here. So having a bit of weight actually is an advantage. This is not really something you want to miniaturize. This is supposed to be used on your bench, put it on the side there, and have easy access to the socket. So that's about it for now on the unit itself. It works very, very well. The previous incarnation worked very well. Obviously, the previous one didn't have the isolation transformer. I wanted this one with the isolation transformer. Using the isolation transformer without limits is easy. You just push bypass and you've got the full isolation transformer coming through, 230 in, 230 out, with the difference that you might just save yourself getting zapped or blowing up a expensive piece of equipment like an oscilloscope or anything, something like that. Again, there's a lot of explanations on why isolation transformers are important for measuring on an oscilloscope. I won't go into that here, but I will go into the logic that led to the build so that anybody who's interested can end up with a schematic, and hopefully the people who've asked me in the past to describe what's inside that funny box I have at the back there will be able to build it themselves if they so wish. Right, let's get on with it. In my radio restoration hobby, I very often have to connect old radios that haven't been used for a while to the mains. And that is a typical situation where you'd probably do well to use something like a light limiter or a dim bulb tester, as they call it sometimes. So in that case, for example, we would have a radio over here. When I speak about radio, I'm usually talking about tube radios, old tube radios, and that would have mains connected. So in a normal situation, this would go straight into our live and neutral of our main socket. Now the main socket would also have a earth connection, mains earth. Now these sometimes do have earth, most often, more often than not they don't, but this is a typical situation. Now if I'm using a radio like this that has not been on for some time and I connect it directly to the mains, I run the risk of having inside here a dead short, which would then probably light up part of the workshop and create some pretty bad sparks that would probably do a lot more damage to the radio than it already has. So what we're trying to do with the dim bulb tester is we're trying to create a limiter of the maximum current that'll flow into that radio when I plug it in like that. So what we do is we put a light bulb, an old-fashioned incandescent light bulb, in series with the radio, with the load, which is in this case a radio. And what happens then is this light bulb, if there is a short on the radio, if you can imagine this is a short, then what happens is that one side of the light bulb's connected to live, the other side of the light bulb goes through the short to neutral, and you have a normal switch. You have a normal light bulb that's connected to your mains. Okay? These light bulbs, in my case here, I work with 230 volts AC. So these will be 230 volt light bulbs, and it's a normal switching situation. What I have effectively done is I've limited the current flowing through that short. If I did not have this light bulb, and if I had a short, all the current that the live could supply to the neutral would try to get through that radio, and somewhere it's going to blow. If I have the light bulb, I've just basically connected a light bulb to my mains. No big deal, right? We do it all the time. Now, why did I want to make this a little bit more intricate, more complicated? Well, the reason is simple. You could build this simply as it is here, and you could have a socket here where you replace the light bulbs. So you could start off with a 100-watt light bulb, for example. If you want less restriction, in other words, if you want to allow a bigger maximum current through, you could make that a 200-watt light bulb. If you want to make more restriction, you could make that a 60-watt light bulb. Okay, so you'd be fiddling around, putting in sockets, putting in light bulbs, taking out light bulbs, and I've done that before. I didn't want to do it here. So what did I decide to do? I decided to add more light bulbs and create the facility of switching them in as needed. So I put in another light bulb, and another light bulb, and another light bulb. I've got 4 light bulbs here. I happen to have a 40 watt, a 60 watt, another 40 watt, and another 60 watt bulb. That gives me a total, where they're all together like it is now, of a 200 watt light bulb. But I want to be able to change that. So what I did then is I added switches to these. So I put in a switch on each one of these, and I can switch them in as and when I want to. So if I wanted to have the maximum restriction, in other words, the smallest current possible going through here, I would use a 40 watt light bulb. So I would only switch that one in. Then my current is limited to, let's see, 230 volts through a 40 watt light bulb. It's about 1/6 of an amp. It's about 170 milliamps or so. That would be the maximum current that could go through that damaged radio, if it were damaged, okay, would be about 170 milliamps. If I put these two in together, so 100 watts, that comes to 100 watts on 230 volts, it's just under half an amp. Okay, 400 and something milliamps. So I would switch those two in. I could switch those two in and get 80 watts. I could switch the 3 of them in and get 120 watts. I could switch 4 of them in, get 160 watts, and I can switch all of them in and get my 200 watts. Okay, and those 4 ranges are fine for me. Now, the way I've built it, I can actually just replace these light bulbs and make them higher if I wanted to do that. But at the moment, that's what I've got. 4 switches, 4 light bulbs. They're all the old type of incandescent light bulb. You have to use those. You can't use the energy saver ones. But that's what I have at the moment. And I went one step further in this particular case because I got that little measuring module, that voltmeter ammeter module, a digital module. And that voltmeter ammeter reads volts and current up to 300 volts AC and up to about 10 amps. So the ammeter part, I want to see what kind of current's flowing through my radio, is fitted here. Obviously, I wouldn't normally have a short on the radio, hopefully. This would in fact probably be the primary of the power transformer. So it's another load. All this is doing is putting a load, which is that resistive light bulb load, in series with this inductive transformer load. But this could be anything, okay? But this way I get to measure the current that's effectively flowing through that. The one peculiarity about this, the way I've wired this, is it comes with a sort of toroid, and the way to measure current is you put the wire that's carrying the current through the toroid, and that'll give you 0 to, I think it's about 10 amps or more. I wanted to read smaller currents, so what I did is I made that wire go through 10 times, which means that, say, 100 milliamps will read as 1 amp. So then I'm basically just changing the decimal point on the meter, and I did that with a marker on the face itself, as you probably see. But that's how I measure the current, and the voltmeter section of that module is over here. So this is the module. It gets its power from this line here and from the mains or the live line. Anything from 100 volts upwards is fine. It starts reading that voltage. The current is then displayed as well. So that's my module, and that's also wired in the system, as you probably saw. The other thing I wanted to do is I wanted to make this isolated. I wanted to add an isolation function to this so that if I'm using a piece of equipment and I'm using an oscilloscope to measure it, I don't want this neutral referenced to ground, because usually if you have this thing connected to ground in there, it'll be connected to one of the power sides. Now you probably see a lot of examples, a lot of explanations on the web as to why this would make your oscilloscope blow up, probably, if you connect the ground the wrong place. But if you put an isolation transformer in here, you resolve that problem. And I just happen to have had one wound. It's a 230 volts to 230 volts transformer. It's a 350 VA transformer, so it allows up to about 1.5 amps, and that goes here. There's my transformer, 230 in, 230 out. The difference is this goes nowhere else. This does not get sent to the ground connection, to the earth connection on the socket that goes to the equipment. So effectively, I can, because my body is referenced to earth ground, if I touch neutral, which internally is basically shorted to ground, I don't get a shock. If I touch the live wire, I get zapped. However, if I touch this guy and I'm not touching that part over there, I don't get shocked. And if I'm not touching here and I touch that guy, I don't get shocked. So effectively, whichever one I touch, I create a path to my earth, and it alternates. It's basically not going to give me a shock unless I touch a difference in potential. So if I touch those two, I'm going to have a sad day. The other thing here is to prevent this thing from overloading. I'll put in a fuse here, 1.5 amps. So if there is a short, and for some reason this thing blows through, I've got that limited to protect my transformer. The other thing I want to do, because this is an isolation transformer, and I sometimes just want to benefit from the isolation function without the limiting function, okay, I've added a switch here. And this switch is my, if it's off, it's my limited supply. And if it's on, if it's closed, it's bypassed. And in bypass mode, I'm only using the transformer as an isolation transformer. I have absolutely no limit in the current. All the current can go through that this fuse will allow. So I have to be very careful, especially when I want to test a piece of equipment and I want to make sure that I allow this limit function to operate. I must make sure that this is open so that the limit function created by these selection of light bulbs is actually going to be used. And of course, there's one other thing. You always want to have the main power switch, and just to make sure it's safe, it's a dual pole switch, so it switches on and off your mains to the transformer. And that's basically all we have in there. And this is the whole system. One double switch, a limit bypass switch, 4 individual switches for the lamps, a fuse, the module, and then of course it goes out to the socket. It's a earthless socket, obviously. Now, the other detail that might be of interest is because of the possibility of making this more visual, I decided to use those neon switches so that when I switch this on, when I close this connection, it actually lights up. And the way it works, those things have got 3 connections on the underside, and they're nubbin 1, 2, and 3. And the way this works is that the signal coming in, the power coming in goes into 1, so that's in. 2 is out. 2 is the switched result between 1 and 2. And 3 is, let's call that neutral. And this works because inside here you have a little neon lamp with its resistor and everything else. And it needs mains power, mains voltage to switch on. So if you connect this neutral, in this case our neutral is actually this line over here, which is not really neutral, but it's the opposite end of the supply. You connect it to there. When your input is connected through from pin 1 to 2, you have across that neon a mains voltage. And because you have mains voltage across the neon lights up. When you switch it off, this line here is cut, so the light switches off. And that just makes it very handy to use because you see visually what it is that you have on and what you don't have on, so that it makes it a lot more comfortable to work with this. You're working with situations where high voltages and pretty high currents are concerned, so being able to see things easily is of great benefit. The other thing is that the power switch is also one of those, except it's a dual, but it's also got the function of lighting up when it's on. And the advantage there is that you've got to have that handy. If something goes wrong, you want to be able to switch it off, and you want to be able to switch both of them off. That's why it's a dual pole. The limit bypass switch is always a risk, because you may forget to open it, in other words, switch it off, and put something in there that's got a short, and then your whole limit function is bypassed, and you'll probably end up with fireworks anyway. So you have to be very, very careful with this guy. On the front panel, I've actually marked an exclamation mark over there. And this is basically it. All that remains is for me to warn you that this is mains voltage. These things are dangerous. These mains voltages can kill you. So if you don't know what you're doing, don't, or get somebody else to do it. All right. Hope you enjoyed that. Please subscribe and click like and all that other stuff. And I'll see you back soon. Thanks for watching.